Hello physics friends, and welcome to our first weekly review. Today, as my fancy almost calligraphy would suggest, we're going to be reviewing waves. In this brief review, we are going to talk about 1, what we define waves to be, 2, some categories of types of waves, and 3, some traits we can use to describe waves, and how to mesh those all together in our future of solving problems with this material. So Colin provided the basic definition of a wave to be an excitation in a medium, and we will be expanding on this with a couple examples, most of which have been mentioned previously, but I just want to recap. First off, we have sound waves, those that are transmitting this physics information to you. Their excitation is the pressure that is modulating in the air, contacting both your ears and the speaker. Next up, we have water waves. Those are excited via height. The water is displaced above its equilibrium position and comes back down, pushing its neighbors aside, making the wave keep going. The medium, as you might have guessed, is water. Simple enough. We also have light waves. Those are transmitting the visual information. Their excitation's a little esoteric. We'll talk about this later. But it is electromagnetic. And their medium, also a bit weird, is the vacuum. They can travel in the depths of space where no man could survive, the true survivalist of the universe. And we will talk about how that works a bit later. It's odd, but interesting, as a lot of things are in physics. So, moving on, let's look at the categories of waves that we're going to deal with. So the broadest of which is just waves. This is our outside of our diagram. So here we can have any sort of thing. It could be a little pulse traveling to the right or to the left. We could draw a parabola going to the right or left. Anything that's just clipping along with some sort of excitation while the medium itself is remaining static, or coming back to the same place. So we have a more rigorous classification as well. These are periodic waves. Periodic, which implies that even if they have some odd shape to them, that shape eventually, it's too late, that shape eventually repeats itself. And it repeats itself in 2 ways. We can see foremost that there is a set wavelength over which it repeats itself, and as time progresses, our wave is going to move through space and eventually line up with itself again, meaning that after that time passes, we have the same shape. So that time that passes between the wave overlapping with itself, we call the period. We have a wavelength and a period. And the wave is moving in some direction with a velocity v. So we can define a few useful quantities that relate to these fundamental parts of the wave. We have our frequency, our inverse of our period. We have our omega, which is the inverse of our period with an angle on top of it, so that we can put it into sine and cosines more easily. And we have our wave number, which is another thing that allows us to easily write down what we put in the sine or cosine. For every theta, or for every lambda that passes, we go exactly 2 pi if we multiply it by k, which we will see shortly. And additionally, we can calculate the relationship between our velocity and our other quantities. That is just lambda, our wavelength, times f, our frequency. Our velocity goes blank lambdas and whatever our frequency is. So if our frequency is 2 hertz, every second we're going to have traveled 2 wavelengths, so you just multiply the 2 together. And you can use these definitions and our expression for v to make any sort of combination you want. Now, deeper within this categorical pi, we have sinusoidal waves. Waves that are beautiful, well-defined wiggles, which I will make a little more room for. This is me artistically expanding this. All right, so these are well-defined wiggles. They are periodic, as we can tell. They are also going to be moving forward in time, so this is like a specific instance in time. And our grayed out version is another instance in time. They have a very nicely defined mathematical form, hence our interest in them, both in terms of solving problems and also describing reality. So we see that they have an amplitude A. They, in some period of time, shift, which I will talk about exactly how much they shift, and a wavelength of lambda, all of which we can see drawn in the picture. So we define, or it might be more apt to say observe, that our sine wave, which is a function of position and time, is equal to an amplitude times the sine wave times k times x, where k is the wave number we defined previously, and omega times t, which is how we shift through time. And this is our common argument for waves. If we have some other type of wave, as we saw in the lecture videos, it can have the same type of argument if it's moving at a constant velocity. But we're mostly going to see sine waves. So here we can use this descriptively. We can say, I have this wave. What is my equation describing it? Then from that equation, you can prescribe like, oh, well, if I want to see what my height is at time 1 second and position 20, I can just plug that in and figure out what that height is. And we have that height for all time and space. Additionally, you can go from a written equation and see if you have something like f1 of x and t is equal to 2 meters times sine of 3 1/meters times x minus 2 1/seconds times t. Then here you could be asked, what are the wavelength, what are the frequencies, and what is the amplitude, which I will show here quickly. We notice that this sucker is associated with A, so this is just A is equal to 2 meters. This is associated with k. K is equal to 3 1/meters, but we don't really have a physical interpretation of k, so we want to say, well, I know that k is defined as we did up here. That's right. Okay, so I'm just going to use that definition of k to relate it back to our wavelength. K is 2 pi over lambda. Plug that in. 3, 2 pi over lambda. Solve for lambda. We have this for lambda. Beautiful. And then we go through approximately the same process if we want the frequency or the period. And this is our omega. I'm going to call it hertz. You can also call it radians per second if you so choose. And we can get that our frequency is our omega over 2 pi, again using what I wrote up here. And that gives us 1 over pi for the frequency. Also, if we want our period, we could say, yes, I know that that's just 1 over the frequency, meaning that our period is pi seconds. Lovely. So that's the baseline level of question that you can be asked about these things. There are a number of ways to utilize your information. Bonus points, we could say, well, we have our frequency and we have a wavelength. This means that we can calculate what our velocity should be. We're learning so much about this beloved wave. We just say, how do you do? These are your parts. That's who you are. Just like how you interact with people. Just kidding. This is not a life science class. We don't know how to interact with people. We just know how to interact with waves. But we did, in fact, get a velocity. So we're still successful at something. All right, yeah, we can get a number of things. A glorious number of things. So this was my first attempt at a summary type video. I would like to know, as I will ask you guys in class, what information I can provide to be most helpful in addition to the lecture videos. These will be recorded on a weekly basis, so like, comment, and subscribe for more. Haha, just kidding. You'll see them on Canvas, as is necessitated by you enrolling in this course. So let me know what you would like to see, and I will hopefully make lots of it. Thank you for watching.